Okay, we're going to continue from where we left off. So we're talking about energy units. The units that we use are joules and calories. 1 calorie is 4.184 joules. That's not exact, but you should remember it. 1,000 calories is equal to 1 calorie, where 1,000 lowercase calories is 1 uppercase calorie. The uppercase calorie represents a food calorie. So there's 1,000 chemical calories in 1 food calorie. And to get an idea of what a calorie is, a chemical calorie is the amount of energy needed to heat up 1 gram of water by 1 degree Celsius. So that would be written as follows: 1 calorie per 1 gram per 1 degree Celsius. Oftentimes in the denominator, you don't write the ones in, it's assumed. So 1 calorie per 1 gram per 1 degree Celsius. To give you a real idea of what a calorie is this: if you were to pick up a 6-pack off the floor to about waist height, that would be 1 calorie of energy. So if you wanted to burn off a calorie of food calorie, you'd have to pick up that 6-pack 1,000 times, or pick up 1,000 6-packs all at once. Good luck. Okay, let's take a look at a problem from the book. You are on a diet of 1,200 calories per day. What is this energy in joules? And here's the strategy. We're going to take the 1,200 food calories, turn that into chemical calories, and then turn that into joules. And for each of these, we need a conversion. So for number 1, we have 1,000 calories is 1 calorie. And for number 2, we have 4.184 joules is equal to 1 calorie. And when we set this up, we start off with the 1,200 calories, and we multiply by the first equivalency first. And for the first equivalency, I'm going to put 1,000 calories in the top and 1 uppercase calorie in the bottom so that the calories cancel. And then, rather than solve the problem at that point after the first conversion, I'm just going to use the second conversion right away. And notice I put the 1 uppercase or lowercase calorie in the bottom so that these calories cancel, and I get 4.184 joules in the top. So my answer ends up being 5.0 times 10 to the 6 joules. That's your correct answer. So 1,200 calories a day is 5 million joules. Okay. Let's take a look at another problem. One food product has an energy content of 170 kcals per serving, and the other has 280 kcals per serving. Which provides the greater energy per serving? Well, the idea here is that we want to convert 170 kcals to kilojoules or 280 kilojoules to kcals. Now, this seems like it's going to be a complicated problem because we have kcals and kilojoules, but we don't have cals and joules like we're used to. But we can overcome this pretty easily. And here's the idea. We're going to convert 170 kcals to kilojoules directly because if 1 cal is 4.184 kilojoules, then 1 kilocal, 1,000 calories, is 4.184 times 1,000 joules. So in other words, 1 kilocalorie is equal to 4.184 kilojoules. So you know that when you have an algebraic expression where you have an equality, to keep it equal, whatever you do to one side, you have to do to the other side. So to keep this equal, what I've done is I've multiplied each side by kilo. And I've placed the kilo in between because these are products, and since they are products, we can put them anywhere we want. Okay, so here's the solution. Start with 170 kcals, multiply by 4.184 kilojoules over 1 kcal, and we get 710 kilojoules. Now, if you left a question like this on a test and thought you were done, you would not get full credit for this. The question is, which provides greater energy? You're not supposed to leave me guessing. Here's what you would need to complete the question. 170 kcals has more energy than 280 kilojoules because 170 kcals is equivalent to 710 kilojoules. You would have to explicitly say that this was more than this and not leave me to figure it all out, okay? All right, next we have making measurements, precision, accuracy, experimental error, standard deviation. The goal is to recognize and express uncertainties in measurements. I'm going to try and do something here real quick. There we go. So, precision. This is how well several measurements of the same property agree. So how do you determine if they agree? And the answer is, a quick and dirty way to look at it is look at the range of measurements. So here I have that example where we've measured something, and here are the three values of measurement. And if you look at the smallest value versus the largest value, the range is 0.2 centimeters. Now, if you look at these three measurements and you look at the range of values, the range is 0.02 centimeters. The smaller the range, the more precise the measurements. 0.02 centimeters is a smaller range than 0.2 centimeters. Now, we are comparing apples to apples because this is centimeters and this is centimeters. If this were 0.2 millimeters and this were 0.02 centimeters, it would turn out that they would have the same precision. Again, if this were 0.2 millimeters, but it's not. Okay, what if you just are comparing two numbers that are averaged from things? What do? So let's say that we had a 1.2 average and a 1.21 average. Which one is more precise? And the answer is the second one here, because we know a number to a smaller number place. This is only known to the 10th, this is known to the 100th, and so when we're looking at the same unit and you know a number farther to the right, that's going to be more precise. Now, how do you actually measure precision? You measure it by something called average deviation, where the smaller deviation is more precise. And we're going to see an example of that in a little bit. Accuracy. This is the agreement of your measurement to the accepted value. So for instance, the accepted value for the density of mercury is 13.6 grams per milliliter. If these were two values that we were comparing to see which one is more accurate, this one is more accurate. It doesn't take a lot of work to see that this value is closer to 13.6 than 13.888 is. However, this value is more precise because we know a number farther to the right. So you don't want to confuse accuracy with precision. Precision just means how well you know a number, but it doesn't mean that whether it's right or not. Accurate is how well it matches the accepted value. Now, accuracy is measured by percent error. The formula for percent error is the error in measurement times 100% divided by the accepted value. For the error in measurement, I use this formula. It's the measured minus the accepted. So the difference in values. You want to start with the measured. That way, if your measured value is larger than the accepted, the difference will be positive and your error will be positive. If your measured is less than your accepted, your difference will be negative and your error will be negative. So the deal is if you get a positive error, your value is too large. If you get a negative error, your value is too small, which tells you a lot about how you were doing the experiment and may give you some hints as to what you need to do to fix it or make it better. And when you look at the absolute value of the error, the smaller the percent error, the more accurate. So 0.1% error is more accurate than 0.2% error. So here's a problem. Suppose a coin has an accepted diameter of 28.054 millimeters. So that's about 2.8 centimeters, which is roughly an inch across. In an experiment, two students measure this diameter. Student A uses a micrometer. Student B uses a plastic ruler. Here's the data. We are supposed to calculate the student's average, use the average to calculate the percent error, decide who is more accurate and explain, calculate each student's standard deviation, which is the real way to measure precision, and determine who is more precise and explain. So just looking at it, we've got to say that probably student A is more precise because we know numbers to the right, farther to the right than student B. As far as accuracy goes, 28.05, we can see that all these numbers are a little bit on the high side compared to 28.05. Here we have some that are on the high side, some are at the low, so it's really hard to determine who may be more accurate. Okay, so the first part, we're going to calculate the average. So we just add up the values, divide by 4, and we get 28.241 average, millimeters average for student A. And we get 27.8 millimeters average for student B. So the percent error for student A is going to be the average minus the accepted value divided by the accepted value, and then times 100%. And we get a 0.666% error. For the student B, we're going to take the average, subtract from that the accepted value, divide by the accepted value, multiply by 100%. So here we get a negative 0.2% error. So what does the positive error on the left mean? It means that this average was too large. What does the negative value on the right mean? It means this value is too small. So that's why the negative and the positive help. Now, when we take a look here, what is a larger percent error? 0.666, or if we round to the 10th, 0.7. 0.7 or negative 0.2? Well, we don't need the negative to compare. 0.2 is smaller than 0.7. B is more accurate. Why? Because the percent error is smaller. Okay, continue with the coin. To calculate the standard deviation, you use this formula, the square root of the sum of the differences between the measured value and the average, divided by the number of samples less 1. Okay, so n is the number of measurements, 1 is 1 less, n minus 1 is 1 less. So if we look at student A, here are the differences, and here's the square of the differences, and here's the sum of the square of the differences. Again, here are the differences. So 28.246 minus 28.241, that's a difference of 0.005. Now, when we're doing these differences, we usually don't take into account positive and negative signs. So these will all be positive as well as these over here. Okay, so we add these together. We get 0.00388. Divide by 3, because there are 4 samples, we divide by 3, and then we take the square root and we get 0.011 millimeters. The way this would be written would be 28.241 plus or minus 0.011 millimeters. So that's our uncertainty, which tells us how precise we are. The smaller that number, the more precise the number we have in front of it. Okay. For student B, we take a look. The differences are 0.1, 0.2, 0.0, and 0.3 respectively between the average and the measured value. When we square each of these and add them together, we get 0.14. Take that value, divide it by 3, take the square root, and we get 0.22 millimeters. So this would be, for student B, 27.8 plus or minus 0.22 millimeters. So because 0.011 is smaller than 0.22, student A is more precise, and this value to the left is more precise. Smaller the plus or minus, the standard deviation, the more precise it is. Now, you don't need to do this on a test. You could just use the standard deviation or the statistics key on your calculator, where you make a list, you put it in there, and then you do stats on it. Okay, mathematics of chemistry. The goals: express and use numbers in exponential or scientific notation, and report the answer of a calculation to the correct number of significant figures. Let's look at scientific notation first. You usually use this for very, very large numbers or very, very small numbers, or numbers where it's hard to write it with the correct number of significant figures. So the format is n times 10 to the e, where n is greater than or equal to 1, but less than 10. So 9.9 is okay, 10.1 is not. 1.1 is okay, 0.99 is not. E is the exponent of 10, and it's going to be an integer, which means it's going to be like a whole number, but it could be negative. So it could be -1, -5, 0, 2, 4, but it's got to be an integer. And the important thing you want to know about E is when you look at this number, if E is positive, the original number, not in scientific notation, is greater than 1. And if that E is negative, then the original number, not in scientific notation, is less than 1. So here are two examples like that. Here the E is negative, which means this original value here is less than 1. And this is positive, which means this original value is greater than 1. Significant figures. Let's take a look. We have some rules here for significant figures, and I'm going to add one more little section here. Significant figures, all digits in a measured property that are exact, plus one that is not exact, but it's pretty well known. It's a good guess, educated guess. So the first rule is that non-zero digits are significant. So this 1 is significant, this 2 is significant, and this 3 is significant. 3 significant figures. That is the only rule for digits that are not 0. And then we have 1, 2, 3, 4 rules for digits that are zeros. So here, tweener zeros are significant. A tweener zero is a zero where there's a non-zero to the left and a non-zero to the right. Not necessarily adjacent to, but somewhere to the left and right. So these two zeros count because they have non-zeros to the left and right. So this has 4 significant figures. Trailing zeros with a decimal are significant. Trailing zeros to me are zeros to the right of the number following the last non-zero digit. So here this 3 is the last non-zero digit. These zeros count because we can see the decimal. So this has 4 sig figs. Here, this number, these are all trailing zeros, and they all count because we can see the decimal. So this has 4 sig figs. So this rule does not have to do with whether or not the zero is to the left or to the right of the decimal. It's really just to the right of the last non-zero, and you can see the decimal. Sometimes we write numbers and we don't put a decimal down. It's implied. For instance, right here, 123 millimeters. The decimal's implied. We don't see it. Now this is the next rule. These rules are for things that are not significant. Zeros that are not significant. Leading zeros are not significant. So if I wrote this number 123 centimeters and started writing zeros in front of it, we wouldn't think those zeros are significant, and they are not. So that's the same here. 3 sig figs because of the non-zeros. Now, look at the number there, 0.123. Do we need that 0 in front of there? And the answer is absolutely not. We don't. It's not significant. Turns out that these two values are the same amount. 123 millimeters is about 5 inches. 0.123 meters, about 5 inches. Okay? So this has 3 sig figs. Now this one might knock you for a loop. This 0.000123 kilometers has 3 significant figures. Turns out that 0.000123 kilometers is about 5 inches, just like these other values. All I've done is change the unit, and it had to move the decimal overs because of that. And we found that in sciences that does not seem to do well for us when we're trying to figure things out, that we can get more significant figures just by moving the decimal over and changing the unit. So we've got a rule. It says leading zeros don't count, ever. Now, this is a rule you may not like, but I don't care if you like it or not. I just care that you know the rule and can apply it. That's what you're going to be graded on, okay? So make sure you understand how to apply this rule, and maybe by the end of the semester you'll learn to love it. And we're going to assume that trailing zeros with no decimal are not significant. They could be significant, they might, who knows? We're going to assume they're not. And then there are numbers that have an infinite number of significant figures. There are 2 categories. 1, defined. So when we say 12 inches is equal to 1 foot, How many significant figures in the 12 inches? Infinite, because it's really 12.000000 forever. And if we write the decimal and we have those zeros that are trailing, they count. So that has an infinite number of zig figs. How about on the 1 foot? Infinite zig figs, because this is defined. 2, counted numbers. Within reason. So let me give you an example. If you went to the CR campus and you looked at the cars in the parking lot, the main parking lot, you could actually count them. 1, 2, 3, 4. I did it one day. There were 21. And then I stopped and I counted them again. There were still 21. That's exact. Not 21.1 cars, not 21.2 cars, not 20.29 cars. It was 21 cars. Now, could you have done that on a regular campus day when the campus is littered with students? And the answer is no, because by the time you get done counting, people may have parked and people may have left. So your number would not be exact. So this has to be something that's reasonable when we talk about counting. We're going to do an experiment where we count the number of drops that we put onto the surface of a liquid. That is something that you should be able to do exactly if you have good technique. Okay, so let's go on. Let's look at these problems here. Express the following in scientific notation and give the number of significant figures for each. I'm going to start with zig figs. Leading zeros never count, so this has 2 zig figs. B is below, not to the right. Take a look here. This has only non-zeros. There are 4 of them, so this has 4 zig figs. Let's look at C. Leading zeros don't count, so this only has 3 zig figs. And this, trailing zeros don't count if we don't see the decimal, so this only has 2 zig figs. Now, to write something in scientific notation, you move the decimal over however many places you need to, so that when the decimal ends up there, you get a number between 1 and 10. So here, I'm going to get 5.4 times 10 to some value here. And this value here is the number of spaces we move the decimal over. So that's going to be a 2. In addition, it's going to be a negative 2 because this initial value was smaller than 1. So my final answer is 5.4 times 10 to the minus 2. And that's going to be grams. Now, how many significant figures does this number have? You look at the n part of it, and you don't care about this part when you're counting zig figs. So this has 2 zig figs to 5.4. So let's take a look at B. And actually, I'm going to be honest with you, the first thing I do is I look at the number and decide, will my exponent be positive or negative? So step 1 here, it's going to be positive exponent, right? And then 2, I'm going to move the decimal over 1, 2, 3 times. And then 3, I'm going to get 5.462 times 10 to the 3rd grams. Okay, let's take a look at C. Number 1, positive or negative exponent? Good. Negative exponent. Let's move the decimal over 1, 2, 3, 4, 4 times. So that's going to be the exponent. And then we get 7.92 times 10 to the minus 4 grams because we decided with the very first step that we should have a negative exponent. How about here? Positive or negative exponent? Positive exponent. And then we're going to move the decimal over 1, 2, 3 times, 3 moves. And then we put it all together, we get 1.6. Now, I'm going to do something wrong here. 0.00 times 10 to the 3 milliliters. How many significant figures in the number the way I've written it? And the answer is 4 zig figs. So this is wrong. How do we write this number so that it only has 2 zig figs? 1.6 times 10 to the third milliliters. And this is correct. 2 zig figs. Okay? All right. Significant figures and calculations. We have 2 different rules for carrying significant figures through calculations. One is for addition or subtraction, and the other is for multiplication or division. For addition or subtraction, the answer has the same precision as the least precise of the beginning numbers. So take a look at this example where I'm doing addition. 14.2 centimeters, this is good to the 10th. Remember how I said when you're looking at a number and you want to know how precise it is, you look at the last digit. This is good to the 10th. Here's 132.14 centimeters. What is this precise to? It's precise to the 100th. Which one is more precise? 100th. Which one is less? 10th. So this is less precise, and this one is more precise. Okay, so we add them together. We get 146.34. Where do we round to? We round to the less precise place, the 10th. So 146.34 centimeters becomes 146.3 centimeters. Okay, multiplication or division. The answer has the same number of zig figs as the beginning number with the fewest. So here I have 1.02 zig figs times 2.12345, 6 zig figs, and we get 2.1 centimeters squared with 2 zig figs. Notice the units also square. Centimeter times centimeter is centimeter squared. So let's look at some problems here. Carry out the following calculations. Provide the answer with the correct number of significant figures. So here we can see that we have 3 zig figs. Here we have 3 zig figs. We don't care about this 10 to the minus 3. We just care about this number here and this number here. So that means that we're going to be allowed to have 3 significant figures when we're done. And here I'm grabbing my calculator. We can kind of estimate the answer here. 0.15 times 6, well, half of 6 is 3, right? So 1.5 times 6.2 is roughly 9. So this answer should come out to be about 9 times 10 to the minus 3. So that's my ish. 9-ish times 10 to the minus 3. So let's go ahead and plug this into our calculator and see what's going on here. 1.52 times 6.21 second EE negative 3. Okay. And we get 0.009. I'm going to put this in scientific notation. And we get 9.4. And you see that says 9.439? I'm going to round it to 3 zig figs, so it becomes 9.44 times 10 to the minus 3. And there's our answer. Now take a look at this one. This is a subtraction. And this one can be very, very difficult because it looks like we've got 4 zig figs here and 3 here, so we want to end up with 3, but that may or may not be right. A trick to doing this correctly is to write them both out in decimal form. So this first one in decimal form is going to be 6217. This is basically 1,000 times 6.217. Here we have 100 times that, which is 523. This is good to the ones, and this is good to the ones. That means when we're done, we're good to the ones. So when their precision matches, that's the best thing of all because you round to where the precision is for both of them. So when we do this subtraction, can you see I have basically 6,200 minus 500, so my answer should be around what, 5,700-ish? But it should be good to the ones. So let's do the work on the calculator. 6 clear 56217 minus 523. And I get, it's actually equal to 5694. And that is the correct answer with the correct number of significant figures. Okay, let's take a look at this last one. We've got 6.27 times 10 to the, that's supposed to be a 3, divided by 5.23 times 10 squared. So the way I'm going to figure this is 5 goes into 6 a little more than 1 times. We'll call it 1.2, right? And here we have 10 to the third divided by 10 squared. That's 10 to the 1. So we're going to get around 1.2 times 10, or 12-ish. So I'm going to say 12-ish. That's my estimate. Okay, so we have 6.217 second EE, 3 divided by 5.23 second EE, 2, and we get 11.887. This has 3 zig figs. This has 4 zig figs. Since this is the multiplication division rule, I use the number that has the fewest number of zig figs, which is 3. So my 11 point, this says 10 to the first over here, and I'm going to change this to flow. So for this 11.887, we're going to report 11.9, 3 significant figures. Okay. Rounding. Do not round until you get the final answer, but keep track of where you would round based on the operation until you reach the final answer. And then when you get there, you're going to have to keep track of where you should have been, and then you round to the proper place. And when you're rounding, you only look at the number to the right of where you're going to round. And if it's a 4, 2, 3, 2, or 1, you round down. If it's a 5, 6, 7, 8, or 9, you round up. Let's take a look here at an explanation for why you only need to look at the next number. So let's say we did some calculation and we decided that we need to round to the ones. So here we're going to round to the ones, which means we look to the right and we see a 4. What do? We round down. So how do we round this down? Well, we take that 4, 9 away and we get 14. And it does seem like from the number we have here to the number we get here that we have rounded down, okay? If this were a 5, we would have made this a 15. And if you had 14.59 and made it a 15, that would seem to be rounding up. So here we rounded down because this was a 4. And that is the proper way to do it. Now, what about this 9? How does that affect anything? And the answer is not one bit. Let's take a look here. This is the wrong way to do it. That's why this says wrong exclamation point. This is so that you learn the lesson of what not to do. Sometimes you learn better from making a mistake than from not making a mistake. So let's make the mistake. So we decide that 9 makes the 4 into a 5. So now you have 14.5. Now that 5 makes that 4 into a 5 and you get 15 centimeters. So we have effectively made 14.49 centimeters, 15 centimeters. This is what I call serial rounding, and it is not a good idea, okay? It's like serial killing, not a good idea. Bad analogy, because that would imply that killing once might be okay, but it's not. Okay, unless it's a fly or a gnat or some sort of bug that really bothers you. All right, why is this a bad way to do it? Well, we need to think about this 49 after the 14, the 0.49. 0.49, this is the 10th and this is the 100th, so this really means 49 hundredths. Clearly, 49 hundredths of a centimeter is less than half. And we don't need the 9 to help us find that out. The 4 alone tells us it's going to be less than half, because this would be 49, it could be 48, 47, 46. it doesn't matter what that second number is. The 4 alone tells us less than half, round down. So that's why we only look at the number to the right of where we're rounding, and we don't look any further. Okay, so here's an example from the book. Calculation that you'll do later in the book. This is the volume of gas, and we're supposed to calculate the final answer. So let me show you what I've done. Here, first of all, I'm getting my ish. So we have 0.12, 0.082 I rounded, 280 because 273 plus 5 is like 278. I rounded it to 280 because I didn't want to mess with it. I took this and I flipped it. So I made the bottom of this times the top and kept this in the bottom. So I have this as kind of my ish. And then I decided I don't like that ish. So I rounded this down to 0.1 and I rounded this up to 0.1. I figured if I'm going to round one down and make my answer too small, maybe I'll round the other one up and make it too big and they'll kind of even each other out. And then I have this 280 here, 230 and 760. And what I decided here is that my 230 goes into my 760 about 3 times, a little more than 3 times actually. Right? So let me think about that. Yeah, a little bit more than 3 times. And this one here, I thought, that's close enough to 300. I'm just going to round it up. Now, since this goes into that a little more than 3 times, that means that 3 is too small. So here, when I round that up, it's too big, and maybe it's a push. So 0.1 times 300 is 30. 0.1 times 30 is 3. 3 times 3 is 9. So that's my ish approximation to make sure I don't mess up on my calculator. Okay, so now let's take a look here. Now, notice what I did here. I did that 273.15 plus 5 first, and I get 278.15. The 5 is only good to the ones, whereas the 273.15 is good to the hundredths. Which is less precise? The ones. So my little arrow tells me that's where I should round to if I were done. But I'm not done, so I don't round yet. Now, when I look at the rest of these numbers, I see I've got 3 zig figs, 4 zig figs. This has 3 zig figs if I had rounded it, but you're not supposed to yet. 2 zig figs, because trailing zeros don't count. 2 zig figs here also, because trailing zeros don't count. Turns out that this is one of those ones that's actually infinity zig figs, but you wouldn't know that yet. So we're going to say 2 zig figs. So that means we round to 2 zig figs. We plug all these numbers in, we get 9.0506. How do we write that as 2 zig figs? Well, I want to keep the 9, I want to keep the 0, but then I need to look to the right of the 0. I see it's a 5, I round up. Zeros become 1 when they round up, so we get 9.1. Here's another problem. Carry out the operations and report the answer in decimal form with the correct number of significant figures. And then I have also write the answer in scientific notation. So what are we going to do here first? And the answer is we're going to subtract these two numbers. So 2.56 minus 2.3, or excuse me, 23.56 minus 2.3 is going to be 21.26. And then we have 1.248 times 10 to the third. However, this is good to the 10th. This is good to the 100th. So what is this good to? It's good to the 10th. Now, am I supposed to round that to 21.3 right now? Nope, I do not. Now, I multiply these all together, and we can do our ish if we want, right? So let's try our ish. This is 1.6 divided by 1.2, which is like 16 divided by 12, which is like what, 1.3? So here it's 1.3 times 21. So 1.3 times 21 is roughly 20 plus a third of 21, which is 7. So we'll call that 27. And the answer ends up being 27 times 10 to the minus 3. 27 times 10 to the minus 3-ish. Or we could write 0.0027-ish, if I've done that right. Okay. So let's plug the numbers in. On 1.68 times 21.26 divided by 1.248 second EE3, and I get 0.02869. Now I've got to ask myself the question, did I mess this up or did I mess this up? And the answer is, when I went here, I messed up. Let's take a look at what I should have done. 27 times 10 to the minus 3. Now, when I want to put this in decimal form, what do? I take a look at that, and since this is negative, I move the decimal to make a smaller number. So if I move the decimal over to make a smaller number, I'm going to move it over 1, 2, 3 times, and that's where it ends up. So this is the place where I made the mistake. I should have only moved it 3 times. I moved it 4 times. Okay, so that means here, when we get the final answer, we have 4 significant figures here, 3 here when rounded, and 3 here. So how many significant figures are we allowed in our answer? 3. So 0.028, right? Wrong. Leading zeros never count. So 0.0286, and that's the correct answer. Okay. Problem solving by dimensional analysis. The goal here is to solve problems using dimensional analysis. Sometimes this is also called the factor label method. Sometimes it's called unit analysis. Basically, it's units canceling. Okay, so let's take a look at problem solving by dimensional analysis. So you know about the identity law in math. It basically says that any number multiplied by 1 keeps its identity. Now, here's this applied in a chemical type setting. So the idea here is that this 12 inches is equal to 1 foot. So that technically is equal to 1, since the amount on the top is equal to the amount on the bottom. And since we have the same amount divided by the same amount, that's 1. So if I take 32.4 feet and multiply by 12 inches over 1 foot, this ratio, the feet cancel, and we get 389 inches. Now, why do we get 3 significant figures? And the answer is we have 3 significant figures here. Since this is defined, we have infinity, infinity, so we get 3 sig figs over here. So this calculation essentially tells us that 32.4 feet is 389 inches. Okay, so let's take a look here. We need to understand why this works. And the reason this works is because when we have a number prefix unit label, it's a product. You can pretend that those things are multiplied by one another. And here's the proof. So if I ask you to add 1.1 centimeter plus 1.2 centimeters and ask you what's the answer, you're going to tell me why it's 2.3 centimeters. I can do that in my head. Well, let me show you mathematically, treating these as products, why that works. So what I'm going to do here is I'm going to factor out a centimeter out of each of these because each of them has a centimeter. So what remains is 1.1 and 1.2, which I'm going to put in parentheses. So I could redistribute that centimeter to the 1.2 and to the 1.1 and make it look just like that. but I wanted to undistribute it. So here I can add what's in the parentheses together. I get 2.3, and then I can remove the parentheses, say I've got 2.3 times centimeters. So that certainly seems compelling that this is a product. And even more compelling is what happens when we multiply these numbers together. Now, what's 1.1 times 1.2? Well, it's 1.31. Now, the centimeter times the centimeter is centimeter squared. Does it seem right that when you're looking at something that has a length and a width, that the area is the unit squared? Absolutely. So here, I'm going to show you mathematically how I treat this. What I do is I rearrange these, because in math, A times B is the same as B times A. That is to say, 1 times 2 is the same as 2 times 1. So it doesn't matter in which order I do the multiplication. So I'm combining the numbers and I'm combining the units, and then I'm simplifying it. And then finally I round. I round to 2 significant figures because the 1.1 and the 1.2 both have 2 zig figs. So here, a number, prefix, unit, label are multiplied. And that means that units cancel. If you have a unit of centimeter in the top and 1 on the bottom, they cancel. So conversion factor. A conversion factor is an equivalence. It's often between the same type of unit. So 12 inches is equal to 1 foot. They're both length. Sometimes they're different types of units. So this is a conversion factor, 55 miles per hour, or we're saying 55 miles equals 1 hour. That is to say that in 1 hour you travel 55 miles, or it takes, in 55 miles, it will have 1 hour of time will have passed. Every equivalence can be represented by 2 ratios. So when you have this 12 inches equals 1 foot, or 55 miles per hour, you can write it as 2 ratios, and both are equal to 1, so that we can use them because of the identity law. So here, if I start off with 55 miles equals 1 hour, divide each side by 1 hour, and simplify, I get 55 miles over 1 hour is equal to 1. If I take the same equivalency, but divide by 55 miles instead of 1 hour, each side by 55 miles, remember the golden rule in algebra, what you do to one side of the equation, you have to do to the other to keep it equal. Simplify, I get 1 hour over 55 miles is equal to 1. So here I have 2 ratios, they're both equal to 1. So I can multiply this against anything as many times as I want, and I don't change the identity of that amount. So let's take a look at a problem here. The problem is to convert 2.98 times 10 to the 8 meters per second to kilometers per hour. So I figured that to turn meters into kilometers, I'm going to need a conversion between meters and kilometers. And because I know what the prefix kilometer means, I can figure out that conversion. And here it is. 1 kilometer is 1 kilometer. And then what I do is I get rid of one of the k's, and I write 1 kilometer is 1 times 10 to the 3rd meters. So here's where I'm going to use the first conversion factor, if you will, from this equivalency. And here I'm going to need 2 conversion factors. So I need 2 equivalencies. And number 2 is going to be 1 minute is 60 seconds. So I can get rid of the seconds. And then I don't want minutes, so I'm going to put 1 hour is 60 minutes. Now, some of you may want to say, well, I'm just going to put together 60 times 60 is 3,600. There's no need to. So let's take a look. Here we start off with the 2.98 times 10 to the 8 meters per second. I'm going to use my first conversion factor and convert meters into kilometers. So I put the meters on the bottom so that they cancel, and I put kilometers on top. So from this conversion here, I decided I wanted meters on the bottom, therefore kilometers had to go on top. And this is equal to 1. And then here, I put the 60 seconds on top so it would cancel with the seconds on the bottom, and therefore 1 minute goes on the bottom. And then to cancel minute on the bottom here, I put 60 minutes on the top here and 1 hour on the bottom. And then when I did my ish earlier today, I got 1.05 times 9-ish. And how did I do that? think I did it something along the lines of this. 6 times 6 is what? 36. 36 times 3 is about 1.05 or 105. So monkey around with this. 10 to the 8th divided by 10 to the 3rd is 10 to the 5th. Or we could say that one of these zeros cancels with one of these 10s. So we basically have 6 times 6 is 36 times 2.98 is, divided by another, the leftover 10 is 3.6, and 3.6 times 2.98 is 10.5, and so we get 1.05 times 10 to the 9th. So I plug all the numbers in, and I actually get this. How many zig figs here? Infinite. How many zig figs here? Infinite. How many zig figs here? Infinite. Why are these all infinite zig figs? And the answer is because they're all defined. Now, we know that this is a 1 second, and we know this is not defined. But whenever you see something along the lines of 1 liter is equal to 1.056 quarts, the idea here is that this is 4 zig figs, but this is infinite. I have seen some books write out 1.056 quarts is equal to 1.000 liters so that they have the same number of digits on each side. Okay, trick question. What's bigger, a liter or a quart? A liter. 1 liter is bigger. How can we tell looking at these that the liter is bigger? And the answer is it's got the smaller number. The smaller number always goes with the bigger unit. Let me show you what I mean. What's the smaller number, 1 or 12? 1. So that means a foot is bigger than an inch. Surprised? I'm not. A liter is bigger than a quart. Now, why am I telling you this? Well, because if you go into a pub and they say, yeah, we offer a liter or we offer the quart, they cost the same amount, which one are you going to ask for? Well, you're going to ask for the liter because you get a little more. Okay. Next, we have a problem here. Oceanographers often express the density of seawater in units of kilograms per cubic meter. If the density of seawater is 1.025 grams per centimeter cubed at 15 degrees Celsius, what is the density in kilograms per cubic meter? Now, the reason we have this in degrees Celsius is because the density depends on the temperature. So in this particular case, they're just throwing out the temperature, but it's not going to be used in the calculation. So we want kilograms per meter cubed, but we have 1.025 grams per centimeter cubed. So the strategy I'm going to use here is I'm going to take that 1.025 grams, turn that into kilograms, and I'm going to take that centimeter cubed and turn that into meters cubed. So that means I need a conversion between grams and kilograms, and here it is, and between centimeters and centimeters, and here it is. Now, here's the solution. First, I multiply by 1 kilogram over 1 times 10 to the minus 3 grams, so grams cancel. Then I use this conversion, and I put centimeter on top so that it'll cancel with centimeter. Now, there's 3 centimeters down here, so that's centimeter times centimeter times centimeter. So I'm going to have to use this 3 times. And when I use this 3 times, my final answer is 1,025 kilograms per meter cubed. This has infinite zig figs, infinite zig figs, infinite zig figs, infinite zig figs, and 4. Now here, I'm showing you something that's wrong. This is correct right here, but this is wrong. This is okay right here, but when you change it into cubing this and cubing that, a lot of people only cube the unit and they don't cube the number. And you can't do that. You got to cube the whole thing. All right. We're almost done. Graphs and graphing. The goals is to read information from graphs, prepare and interpret graphs of numerical information, and if a graph produces a straight line, find the slope and equation of the line. So I'm going to go over this quickly because it is review for you. So when you draw a graph, You want to make a list of the points. You want to draw the axes so that the largest number is close to the top of the axis or the farthest point from 0. Draw tick marks evenly spaced. Label the tick marks, but not too crowded and not too sparse. Label the axes with the type of unit and the unit. So your type of unit might be mass, and you might be looking at grams. Or your type of unit might be volume, and you're looking at milliliters. Plot your points. Draw the best fit line to determine its slope, which I'll go over very quickly because it's review, and you title the graph. So another thing you want to do when you're graphing things is you want to draw a large graph. So here's a piece of paper. This tiny itty bitty little graph is no good. You want a big full page graph. So here's some data. You drive from McKinleyville to Eureka. It takes you 23 minutes and you travel 15.4 miles, probably because of that corridor. And then you drive from Eureka to Carberville, and it takes you 69 minutes to go 67 miles. So you're going close to 60 miles per hour there. Then you drive from Carberville to San Francisco, and it takes you 215 minutes to go 204 miles. Graph the data and determine the equation of the line of best fit. So here's the graph that I drew for you. The title is distance versus time driving. And on the y-axis, I put the distance. And on the x-axis, I put the time. And notice the tick marks are 50, 100. I didn't put a 150 there because that'd be too crowded, and 200. And here's 0, 50, 100, 150, and 200. Now, it's important to note that I have 5 squares here for 50, and I have 4 squares here for 50. That is okay. More importantly, I've used the full scope of this graph. Here are my 3 points. They're the little dots. And here's my line of best fit. Now, why did I draw my line closer to this top dot and farther away from the bottom dot? Well, in my opinion, that bottom dot represents a smaller length of travel and probably less representative of my overall speed, if you will, for this whole trip. So I tried to make the dot closer to the longest part of the trip and maybe farther away from that. So this is what I got. And to get the equation of the line, you'll notice I have these 2 crosses because it's very easy to pick up the points there. So my 2 points are 162.5, 160, and 87.590 using the XY format, where X is the horizontal axis and Y is the vertical. And to get the slope, you do the change in Y over the change in X. So here are my Y's, 160 and 90. Here are my X's, 162.5 and 87.5. And here's the value for the slope. To figure out what B is, you plug in the value for the slope and you plug in an X value and a Y value. So I used 90 for my Y value and 87.5 for my X value and figured out what B is. And here's the equation of the line using the Y equals mx plus B format. But I thought I'd do one better because Y is really distance and T is really time. So I used the letters D and T. Okay. Lastly, problem solving in chemical arithmetic. Goal, solve problems using a systematic approach, incorporate quantitative information into an algebraic expression and solve that expression. So basically, here it is. Read your problem carefully. Find out what it's asking. Reread it. Write out the information given. If given as a ratio, write it as an equivalence. That way you have no problems putting either side on top. Determine a likely starting spot. And map out connections between the start and the finish using equivalencies and whatever else you may need. So here's a problem where a mineral has a density of 0.875 grams per centimeter cubed, and you spread 0.75 grams of the oil over the surface. How thick is the oil layer? So also helps to draw a picture. So here's my water with the oil on it. And this question mark here signifies that's what we want to figure out. How thick is that? And the diameter is 21.6 centimeters. So here I've redrawn that oil as a disc where the thickness is on the side and the area is on top. Now for this disc, the volume is the area times the thickness. Now, what is the area of a circle? It's pi r squared. And so we could figure out the thickness by getting the volume and dividing by pi r squared. So these are things that we would like to know. What is pi r squared and what is the volume? Okay? All right. So here's how I went figuring out what the area was. I know that the radius is half the diameter. So I get 21.6 centimeters divided by 2, and I get 10.8 centimeters. I know that the area is pi r squared. So I do pi times 10.8 squared. And notice we get centimeters squared here, and we get 366. You can even do the ish, right? That's 11 times 11, which is what, 121? Or what's 121 times 3? Well, that's 363. So see 363-ish, and that's what we get. Now, what is my little arrow here for? It's to remind me of where I need to round when I'm done. Here, there's no issue because this is good to 3 zig figs. This is good to 3. But here there is an issue. So the arrow tells me I'm good to the 1s. Now for the volume, I start with the 0.7 grams of oil, 0.75 grams of oil, and I multiply by the density, but I put the 0.875 grams on the bottom so that the grams cancel and the 1 centimeter cubed on the top. So here we get 0.857 centimeters cubed, and again my arrow pointing to where I would round. Now, to get the thickness, I take the volume divided by the area. I get this, and I get 2.3 times 10 to the minus 3 centimeters, or 0.0023 centimeters. 2 zig figs because of this 0.857, because of this 0.75. Okay, that's how you do it. All right, thanks for listening.